research contributions focus on blockchain-enabled authentication systems with secure key agreement protocols, smart agriculture security, IoT-enabled healthcare privacy, digital twin security, metaverse security, drone-assisted offshore communication, lightweight authentication frameworks for intelligent transportation and industrial systems. Her work mainly concentrates on emerging technologies such as blockchain, edge computing, AI, and procurement protocols to design scalable and secure physical infrastructures. She has also presented her research at leading international conferences including IEEE, ICC, IEEE Platform, IEEE Infocom workshops, ASEAN Census, and ASEAN ICCCS. And she also authored chapters on security and privacy in cyber physical systems and blockchain-based fog computing, which are published in CRC Press and Springer. With her strong academic background, impactful research contributions, and international experience, Dr. Anusha Vangala is making significant contributions to the field of next generation cybersecurity and secure intelligent systems. We are delighted to have her with us today and are confident that her session will provide valuable insights into secure and privacy aware industrial systems. On behalf of the organizers, faculty members, researchers, and participants, I extend a heartfelt welcome to Dr. Anusha Vangala and invite her to deliver her expert talk. Thank you, ma'am. Welcome to our activity.
Just magnet. Okay. Hello, audible, no? Yellow pipe.
Is that comfortable? Yeah, I think ID card. That is one.
This is fine actually. Only thing is I don't want this tree maybe. So it's better.
Can you just check once?
Hello, am I audible? Hello? Am I
Yes,
audible?
ma'am, you are audible, ma'am.
Okay. ఇది కూడా పెట్టుకోవాలా ఓకే వైర్డ్ ఇక్కడ పెట్టుకోమంటారు ఓకే వెయిట్ సెకండ్ ఏం చెప్తామంటే చున్నీ ఎలా పెట్టచ్చు అటు తెచ్చు
ఇలా పెట్టేసుకోమా
ఇలా పెట్టేస్తే దీనికి పెట్టేసుకో ఓకే యాక్చువల్లీ నేను అనుకున్నాను అప్పుడు వైర్లెస్ ఉంది మైక్ తెద్దాం అనుకుని సర్లే మీరు అరేంజ్ చేస్తారని ఇది hold it with hand. Okay.
When point is there, no?
Okay. Comfortable. Okay. Okay, na?
Otherwise, you keep this mic to this ID card.
Okay. Actually, ఇది బానే ఉన్నట్టు. Hello, am I audible to everyone? Online and offline, am I audible?
Online is
Yes, ma'am. Online audible, ma'am. Thank you.
Offline.
offline.
Hello, am I audible now?
Yes.
Yes, madam. Audible, madam.
Okay. Yes, so good afternoon, everyone. So we are here for a session on privacy preserving security frameworks for industrial environments. Long name, but we'll break everything down and see how we are going to actually give security and privacy together in industrial environments specifically. Okay, so we'll start with the first idea. We are talking about this idea called privacy, for which will Lisa point out, close your pointer. So yes, so first we'll talk about the concept of privacy. What exactly is privacy? So privacy basically means that we have first, in an automated network, the goal is to move towards an automated network. We are right now progressing towards it. We do not yet have an automated system, complete automated system. So what we want here is, when we talk about privacy, we are collecting huge amounts of information from our physical environment. How are we doing that? We have different kinds of sensors, we have different kinds of devices which collect information from their environment. So all of this information, they're collected, processed, and shared. And when they do that, this data, which is sensitive, physical, real world data, it has to be collected, processed, and shared by making sure that the sensitivity is maintained. How do we maintain sensitivity? We're talking about identifiable information. When you have raw information that is identifiable, identifiable to whom? Identifiable to the devices, identifiable to the users, identifiable to any or like the location, identifiable to the environment. Okay, any information that can be traced back to the environment, to the users, to the devices, that loses privacy, right? So so basically what we want to do here is, we want to be able to process and do all of this collection, processing, and sharing of the data by not being able to identify that data to the actual location, device, environment, or the users. Okay, so that will ensure that we have privacy. Now, how do we achieve this privacy? There are three cryptographic pillars in an IoT and digital twin environment. The first one is confidentiality. How do we achieve confidentiality? We want to make sure that any data that is either at rest or in processing, it is not exposed to unauthorized people. That is confidentiality. The second is anonymity. So here we want to make sure that the identities of the devices or users, identity of the different entities involved, they are completely decoupled with the data that is fed into the twin or the IoT environment. Okay, so what are we decoupling? The identities and the data, they have to be decoupled. We can take the data, perform any kind of processing on it, but this data should not be traced back to the different identities. That is anonymity. Next is data integrity. What are we trying to do here? We want to see that there is no modification or tampering of data. That is specifically the data integrity. So these are the three kind of goals that we want when we want to achieve privacy in IoT and digital twins. Now, how are we doing this thing? How do we achieve it? There are multiple different technologies. These are called PETs, privacy enhancing technologies, or PPTs, privacy preserving technologies. There are various ways of doing this. Now, for different kinds of applications. The first one is fully homomorphic encryption. What we want to do here is, we want to see that, let's say we have cloud servers. Cloud servers is usually the most common application where homomorphic encryption is applied. So what we want to do here is, we want to perform computations on the encrypted data. Data is encrypted and you can perform computations and processing on encrypted data and get the same results as you get on unencrypted data, which means you're preserving the privacy of the data during processing. So the entity which is performing those computations is doing it blindly. It does not know what data it is working on, but it is still giving the correct, accurate results. The second is secure multi-party computation. You have distributed entities. Whenever you talk about IoT, it's or digital twin environment, so you have different kinds of sensors there. So different distributed entities, they jointly perform some computation together. That's how the name comes, multi-party computation, and it is secure in the sense that you're not revealing the inputs that are being given to the computation. Okay, so the inputs given to the other party are not known to one party. Each party only knows the inputs that it is getting. It does not know the inputs given to the other parties. So that's how you maintain privacy there. Next, you have differential privacy. Here it is trying to look into adding some noise or randomization into the data set so that the actual data set that goes into the system cannot be extracted correctly. Okay, that's differential privacy. So what we are trying to determine here is you have you have group of data, you have like a collection of data on which you can perform different computations. But if you pick out a single thing in this data and say who does it belong to, you cannot answer it. But you can get a results on this collection. That's what differential privacy is. Once again, you cannot pinpoint or trace it back to one single entity. The next thing is zero knowledge proofs. So zero knowledge proofs, they allow you to basically one party can prove some specific claim to the other party. There is one party which is claiming something. Whatever it is claiming, it can prove it to the other party without revealing any underlying secret private information. That's zero knowledge proof. Okay. So in the talk today, we are going to focus specifically on zero knowledge proofs and how it works. Okay. So now when we talk about, so you see, as you see in the slide, there's the privacy preserving itself is a huge area of research. Each of these is a huge area of research. Okay. So today we are going to focus specifically on zero knowledge proofs. So first of all, zero knowledge proof is a proof. What is a proof? Mathematically speaking, it's basically a sequence of deductions. Mathematically, when we say we want to prove something, it's basically a sequence of deductions. You have basically some standard rules, standard axioms or assumptions, which you keep applying one after the other logically, and then you arrive at a conclusion. That's what a proof is mathematically. In cryptography, a proof is an object. A proof is considered a specific object. It could be a protocol also, a protocol or an object. What does it do? It is basically saying we have a verifier is going to verify that a particular statement is true except with negligible probability. Now you have to understand we are talking about a computationally bounded verifier here. We are basically trying to prove that a particular statement is true with some negligible probability. This is the idea. So it's an object where you're trying to, where the prover has given a statement which has to be verified by a verifier such that with negligible probability, it is always true except for negligible probability. That means with very high probability, it is true. And we're specifically talking about computationally bounded verifier. We'll talk about this in detail. So basically, in cryptography, it's not a logical derivation. It's a prover and verifier. It's kind of the prover and verifier doing a sequence of actions to verify a particular statement. Okay. So now, what does a proof system consist of? So we have a prover, Peggy. Well, you know, cryptography is all about how Alice and Bob and their friendship and how they talk to each other. In proof systems, we have Peggy and Victor. Okay. So Peggy here is the prover, and we have a verifier Victor. There is a claim X, which is a statement that is supposed to be proved. So the prover P performs a computational task. What is the task? It generates the proof. Generating the proof is the task it performs. And then in this proof generation, what is actually happening? It is going to generate something, some statement to the proof P that relates this statement to P. In the proof generation, the statement X is related somehow to the prover P. Okay. And then the verifier, the computational task he is doing is verifying if that statement X is actually related to P or not. Okay. So now this proof, the actual proof is denoted by pi. What does it actually contain? It's basically a set of cryptographic values. Okay. That's what a cryptographic proof is. In mathematics, it's a sequence of deductions, but in cryptography, it's basically a set of values. These set of values, which are denoted by pi, is the proof which helps the statement X to be related to the prover P. Okay. Now there are different kinds of proof systems based on and different complexity classes here. So first we have something called NP proofs. Sorry. So we have something called NP proofs, which are non-deterministic polynomial proofs. So these are non-deterministic and computationally unbounded. You have deterministic, whereas the verifier is deterministic and polynomial time. which means we'll talk about this again in detail. Then we have IP proofs, which are interactive proofs, which means it's non-deterministic and computation bounded, but the verifier can add randomness and there is an interaction involved. These are interactive proofs. Arthur-Merlin proofs are also interactive proofs, but a special type in them where there is a flipping of coin allowed using randomness, but victor cannot keep any secrets. The verifier cannot keep secrets. Okay. You also have other types of proofs like PCP, MIP, and exponential proofs. These are other different types of proofs depending on the classes, the different complexity classes and kind of. We are basically trying to say what is a prover allowed to do and what is a victor allowed to do, and based on that, based on their capabilities, we have different kinds of proofs. We are going to specifically focus on NP proofs for today and a little bit of basically IP proofs, interaction proofs. Okay. Now, first of all, to understand NP proofs, we have to understand what is NP class. This is something basic coming from algorithms. So you know what is polynomial time, right? In NP class basically means non-deterministic polynomial time. So what is polynomial time? You perform a task in polynomial time of the input, polynomial size of the input. Okay. So when you say non-deterministic, what does that mean? It means there is unpredictable behavior over different runs of the same input. If you give the same input multiple times, it gives different outputs. For the same input, if an algorithm gives the same output, it is going to be deterministic. For the same input over multiple runs, if it gives different outputs, then it is non-deterministic. Basically, that's what that non-determinism means, which means the outputs will change over multiple runs. Now, what is NP? NP basically means it's a set of decision problems where solutions can be verified by the computer in polynomial time, but finding the solutions is difficult. So your NP basically means that you have a problem. If I give you the solution, you can verify. You can verify in polynomial time and tell me whether the solution is right or wrong. Verification is done in polynomial time. Verification is easy, but generating the solution is difficult. That is exactly what NP is. And these are some examples. These are basic concepts from algorithms. I believe you're familiar with that. But this reflection is required to understand what it means. So NP is basically verification is easy, but generation is difficult, right? Now, if a decision problem, if it is in VPP, if it is in VPP class, that means it is correct most of the time. When you execute it multiple times, for most of the time it is correct. Some of the times it may be wrong, and that is acceptable. Yes, this basically is saying that decision problem is in NP if you can check the solution, if there exists a solution, right? Now, how do you verify if a proof system is efficient? You say that if the verification process is efficient, then the proof system is efficient. Efficiency means it can be done in polynomial time, right? So now, what is an NP proof? We talked about what is NP class, how NP class works. We talk about now what an NP proof is. So here we are talking about non-deterministic polynomial time, which is a class of proofs. Here we are talking about there is an asymmetry here. Verification is easy, but generation is difficult. Now here what's happening is every language, a particular language is in NP if it has an efficient verification procedure. Okay, this is something we saw in the previous slide. If I give you a statement, you can verify in polynomial time whether it belongs to NP or not. Okay, which means only if the statement is correct, only if the statement is true, its proof can actually be present in NP, right? So only correct statements, that is X, which belong to L, only statements which have this correct proofs, they will belong to these proof systems. Okay, so mathematically, how do we determine that? So we have this language L where you have X, which is the claim, the statement to be proved. You have W, which is a witness. We'll talk about witness in detail a few slides later. You have a witness such that whenever there is a witness, it means that this particular X belongs to L. This is what it means. You have a statement to be proved. That statement is belongs to this particular. So this language consists of all the statements which are true. And how do we say that they are true? When they exist a specific witness, and such that there is a relation that exists between the statement and the witness. Okay, so witness is a value. You have a statement which has to be proved true or false, and the statement, if it is in NP, it means it will have a proof system. When it has a proof system, there will be a secret witness. Witness, for now, you can think of it as a secret. Okay, so it will definitely have a witness. So whenever there is a witness, it means the statement X belongs to this particular NP proof. So here you can say that whenever it is recognizable by this polynomial time recognizable language, which is basically saying the same thing as having an efficient verification procedure. So when you say efficient here, polynomial time recognizable means that whenever you say that this X and W belongs to RL, what does it mean? Which means the size of the proof is less than or equal to is basically upper bounded by the polynomial size of the statement. The size of the witness is upper bounded in polynomial time, polynomial size of the statement. Okay, you take the size of the statement, and the witness should be less than or equal to polynomial size of the statement. This is what an NP proof really means. Now just let us switch gears and let's talk about interaction, the concept of interaction. Okay, so zero knowledge proof, we started with the idea of proof, then we talked about what is NP, then we talked about what is NP proof. Okay, now non-determinism means over multiple runs, multiple outputs will be generated for the same input. That's what non-determinism is. Okay, and if it is being done in polynomial, if the verification is done in polynomial time, then it is NP, non-deterministic polynomial time. Verification is polynomial, but generation is not polynomial. Okay, now let's switch gears. We'll talk about interactive Turing machines. So in a deterministic, if you look at this particular thing there, this is exactly what an interactive Turing machine is. So here you have a deterministic multi-tape Turing machine. Okay, so what does this contain? It has an identity. The identity is denoted by sigma, which is binary, either 0 or 1. Why binary 0, 1? Because you have two tapes. One of the tapes is 0, the other is 1. You only have two tapes. Next, there's a read-only tape. One of the tapes can only read, reads the input X. It has a read-only random tape which generates randomness, which generates random input. So there is one input which is a statement X. The other input is the random input to introduce randomness into the system. It generates some random values. Next, you have a pair of communication tapes. Basically, one is read-only, one is write-only. So there is message sent and message received here. Now what happens? So there is a switch tape along with this. So whenever there is one, so how does interaction occur? When one is speaking, the other is writing. One is reading, the other is writing. So whatever is written by the write tape is being read by the read tape. So then when it has to respond, they switch out. Okay, so that's why to switch this thing, we have a switch tape. Now, so if the switch tape basically contains the identity. So you have identity 0 and 1 here, for example. So whichever tape is active, the identity of that is present in the switch tape. Okay. Now the movement is always from left to right. So here it's going in the left to right direction. That's the movement. Now let's see how this actually works. So the joint computation in the sense that the two ITMs, the two Turing machines, they are linked together if they have opposite identities. If the input tapes are coinciding, the switch tapes are coinciding, and read-only coincides with write-only. If the read-only tape coincides with the write-only tape, then whatever is being written by one tape will go into the reading of the other tape. That's why the write of one is connected to the read of the other. Okay, this So that way the Turing machines are actually interacting. This is the most important point in the interaction part of the interactive Turing machines. Okay. So when this happens, now we are talking about three very important points. Whenever one machine is active, the other is idle. This is very clear, right? At a given point in time, only one of the tapes can be active, which means when the right tape is active, it is only writing. The other tape will read after that. Okay, only one of the tapes is active. The second is on a common input, on a given common input, how do you represent the joint computation? It is basically a pair of values. What values? The inputs of both the tapes, the outputs of both the tapes, the random inputs of both the tapes, and all of these basically configurations, and also the switch tape. So all these configurations for the first tape and second tape, you put them as a pair. That will be the list of configurations, and that represents a computation, joint computation. Once again, we always talk about, when it comes to computer science, it's always values. How do you represent a computation? Computation is represented as a sequence of pairs. You have a sequence of pairs of values. Why do you get pairs? Because you have two tapes. In the pair, you take one value from the first tape and second value from the second tape. Let's say you take random inputs. The random input of one tape and the random input of the other tape become one pair. That is one value. Then read tape. Random input, the read only value of first tape, read only value of the second tape. That's another pair. Write tape. Write only value of the first tape, second tape. Another pair. So this way you create a sequence of pairs. And when you keep performing these computations, you'll have a sequence of all these pairs for each of these computations. For the first action, you have read, write, and random inputs. Second operation, third operation. So you have sequence of all these pairs. That is the configuration, which is representing the computation of these, the interaction. That is the interaction that is being represented. Okay. Now, how does it actually work? Whenever the first tape halts, when the switch tape itself belongs to that identity, when the switch tape has the identity of that particular machine, then there is a halt. So in normal operation, when this is happening, the switch tape consists of basically, when the current tape is active, the switch tape usually consists of the identity of the other tape, so that we know that it has to switch to the other one. That's how the name switch comes in. Switch always tells which tape it has to switch to next, right? But when in this entire process, when the switch tape consists of the tape that is currently active, it means it will halt. After this, there is no other switching that is going to happen. Okay, that's what this is. So now at that point, when this happens, we look at what is the output, and that is going to be the final output of this interactive Turing machine. Okay, this is a core concept to understand how interaction occurs between two machines. Okay. Now, at that point, we identify the output, and then we look at the time complexity in terms of the size of the input statement that we gave. If it is polynomial, then it is a polynomial time computation. If it is not polynomial, then the computation and the interaction is not polynomial. Okay. Now we talk about, now that we understand the basics of interactive Turing machines, we move into interactive proof systems. Remember in the table, the first one said NP proofs. We talked about what is a proof, what is a proof system, what is NP, and what is NP proof. Then the second point it talked about was interactive proofs. So to understand the interaction, first we saw what is an interactive Turing machine, how two machines actually interact. Now we are going to talk about what is an interactive proof system. So here you see interactive proof systems, once again, they capture what can be efficiently verified via an interaction with the outside. Okay. So since it's a proof system, once again, the verification is very important. We saw that efficiency of any proof system is basically efficiency of the verification procedure. You see, if the verification process is efficient, what does efficiency mean? When do we say something is efficient? It is in polynomial time. We call something as efficient when it is being done in polynomial time. Okay. So if the verification is efficient, which means verification can be done in polynomial time, then it is a then that is the efficiency of the proof system, which means we have a polynomial time proof system. Now, if that proof verification can be done via an interaction with the outside system, via some interaction, then it is called an interactive proof system. Okay. Now let's see how this occurs. So interaction basically means message exchanges. So how are these message exchanges being done? The total time that is being spent by the verifier is polynomial in the input, common input. Okay. The total time that is being spent by the verifier, it is polynomial in times of the input. Now let's say how to accept and reject. On what basis are we going to accept or reject? It is a probabilistic system. How is it probabilistic? We either accept or reject the claim in a probabilistic manner, and we have a bounded error probability. We have some error allowed in that. Okay, that with this much probability and this much error, we are accepting this particular statement X as true. That is what we are going to say. Okay, now, so here once again, just to summarize, our verifier is probabilistic polynomial time. Since efficient procedures are probabilistic, are PPT algorithms, probabilistic polynomial time algorithms, and then a prover. For the prover, there are no restrictions. We say the prover has no resource bounds on computing power for either completeness or soundness conditions. Now, what are these completeness and soundness conditions? We'll discuss them in detail in a few slides later. Okay, which means the prover, we expect them to have unlimited resources so that they can generate the proofs. Because we saw that proof generation is difficult, that's why we are giving the prover unlimited amount of resources. But proof verification, it has to be polynomial time. So that is the restriction we put here, that verifier algorithm must definitely be polynomial time algorithm and it is probabilistic. Okay, that's how we define our efficient verifier in the proof system. Now, what are the conditions? The completeness conditions we are talking about, very simple. In a proof system, if I say that something is true, okay, if the claim X is, if the statement is true, it should be verified as true. If the statement is true, it should be verified as true. If the statement is false, it should be verified as false. Basic concept. These two conditions are called completeness and soundness. True statement must always be verified as true by an efficient verifier. That is completeness condition. False statement must always be verified as false. That is soundness condition. But if a false condition is verified as true, that is wrong. We don't want a false statement to be verified as true. Right? That should not be allowed. Right? So these are basic conditions. Now the first thing which says that true statements should be verified as true, that is with respect to the prover, prescribed prover. Soundness conditions, it should be for all the provers, all potential provers. You understand? So if a prover has given a statement and says that true statement is supposed to be verified as true, with respect to one prover we can do it. But if a false statement you want to verify, there could be many false statements. You could have a cheating prover who is trying to say that a false statement is true. Right? So with respect to